Question 1a, we're asked to complete a truth table. So not P, that's the opposite of P, right? So here's the P column. So not P would be false, false, true, true. Not Q, opposite of Q, which would be false, true, false, true. This means P, PRQ, so PRQ. Only time we have a false is when both statements are false. So in this case, we'll have a false here, and everything else would be true. Not PRQ would be the opposite of this column, which would be false, 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 true. And now not P and not Q, which would be combining these two statements. And the and, no, the and, the only thing we have true is when both statements are true, so this would be true. Everything else will be false. So now we're asked to state whether the statements not PRQ, that's this statement, and not P and not Q, we're asked to state whether these statements are logically equivalent, and the answer is yes, both statements are logically equivalent because they have the same truth values. Alright, so both statements are logically equivalent. Note the truth values are the exact same as they go down the rows. Next, so we have a binary operation. Note the symbol here is a circle with a plus sign within. Is defined, and the set of real numbers are, and it represents a A, and this symbol represents a 2 times the first term plus 3 times the second term. That's what it's saying. So this is 2 times the first term, which would be 2 times 5 plus 3 times the second term, 3 times 2. That's 10 plus 6, so the solution is 16. Next, we're asked to prove that the binary operation is closed. Remember, let's recall that A. Alright, so it's 2A plus 3B, so we're asked to prove that the operation is closed, meaning once A and B are real numbers, the result will always give you a real number. Alright, so notice if you have a real number, so remember A was a real number. A was a real number, which means that 2A is a real number. Note also B was a real number, which means that 3 times B is also a real number. And of course, if you add 2 real numbers, so hence the sum of any 2 real numbers would give you a real number. So therefore, the binary operation here is closed. Alright, meaning as long as A and B are real numbers, then 2A plus 3B will always result in another real number. Alright, so it's closed. Next, we're asked to determine whether the binary operation is commutative. So recall that A, the binary operation, meant 2A plus 3B. Now, if the operation is commutative, I mean the order is not important. So let's find B, symbol here A. So of course the operation says multiply the first term by 2, so that's 2B, and the second term by 3, so that's 3B. So note that 2a plus 3b is not equal to 2b plus 3b. Hence, the order is actually important. So it's not equal to. Therefore, the operation is not commutative. Because if it was commutative, remember, if commutative, then that would be equal. And since I'm putting a note there, and since they're not equal to each other, then it's not commutative. So now we're on to part C. So given that the expression, so this product here of these three brackets is always equal to cx cubed plus 10x squared minus 2x minus 10 is an identity. So let's expand the bracket and equate. So we're going to expand brackets and equate coefficients. Alright, so the first bracket. So let me just write out everything. So we have 2x plus a. And I'll be expanding now x minus 1 times bx plus 1. So x times bx, that's bx squared. X times 1, that's 1x. And negative 1 times bx, that's negative bx. Negative 1 times positive 1, that's negative 1. And all of that is an identity to this term over here on the left hand side. Alright, let's continue with this expansion now. So 2x plus a times this bracket. So 2x times bx squared, that's 2bx cubed. 2x times x, that's 2x squared. 2x times minus bx, that's minus 2bx squared. 2x times minus 1, that's minus 2x. And continue. So a times each term. So a times bx, that's abx squared. A times x, that's ax. A times minus bx, that's minus abx. And a times minus 1, that's minus a. And all of this is identical to cx cubed plus 10x squared minus 2x minus 10. So now we can equate coefficients of like terms. Now first I'm going to equate the constants. Notice the only constant here. The constant of course will be the term that is without x. So notice the constant over here. So I just put what I'm doing here, equating constants on both sides. So on the left hand side, the constant here is negative a. Notice negative a does not have a term in x. And the constant over here, this term that does not have an x over here, is minus 10. So minus a equal to minus 10, which means that a is equal to 10. Let's equate coefficients now for the terms in x. Notice the terms in x, there's minus 2 terms in x. So that's what I'm doing. So equate coefficients for terms in x. So now notice the terms in x. On the left hand side, there's minus 2x. There's a, there's minus AB. And the terms in x on the right hand side is just minus 2. Now we know the value of a is 10, so we can replace a with 10. So this is minus, so we put this is minus 2 plus 10, since the value of a is 10, minus 10b is equal to minus 2. And of course we can solve. Now, if we solve this, we can add 2 to both sides. So we'll end up with 10 minus 10b equal to 0. Which means, let me just separate that. So 10 is equal to 10b. Divide both sides by 10. So b is equal to 1. Now let us equate coefficients for x squared and x cubed. So now we are equating coefficients for x cubed. Let's look at the expansion again. For x cubed, notice for x cubed, on the left hand side, coefficient here is 2b, and on the right hand side, the coefficient here is c. So it's 2b equal to c. But remember the value of b is 1. So 2b would be 2 times 1. So the value of c is 2. And that's it. Part D, solve a log equation. So notice the bases are different. So change of base problem. So usually it's a wise idea to convert everything to the smaller base. Doesn't have to, but I guess it's always sometimes the best option. So I'm going to convert everything to base 2. So this log, remember, so log. So I just change the base 4 to base 2 upon 2x plus 2. But remember, once you change a base, you have to divide by log. And again, base 2. And what was the old base? 4. Alright? Minus log 2 x plus 1. Okay. And now what's the value of log 4 base 2? If you could let me just put it up here. Just explaining why or arrive at the value for log 2 base 4. If we let it be equal to x, then it means that 2 to the power of x is equal to 4. So 2 to what power give you 4? 2. So x is 2. So log 2 base 4 is 2. So this can be rewritten as log 2x plus 2 upon 2, since log 4 base 2 is 2, minus log base 2x plus 1, right? Equal to 1. And now we can try to get rid of this denominator by multiplying each term by 2. So let me just write what I'm doing. So I'm going to times each term by 2. So 2 times this term here. So 2 times this term. 2 times this term. And 2 times the right hand side, right? So I'll end up with, alright, so we end up with, and then 2 times this term. We now have minus 2. And then 2 times the right hand sides. So we end up with that. So now you will recall one of the laws of logarithm. This 2 we can bring use of the power here. So log 2x plus 2 minus, and then this 2 we can make it the power there. So this is x plus 1 to the power of 2 is equal to 2. So now Remember one of the laws of logarithm, log a minus log b is equal to log a over b. So we can rewrite the left hand side as 2x plus 2 upon x plus 1 all square. So the left hand side can be written as that, equal to 2. Alright, logarithm says log a minus log b is log a upon b, and that's the rule we use to rewrite the left hand side. Now, so law of logarithm also, so 2 to the power of 2, the base to this value is equal to what we have in the bracket here. So 2x plus 2 upon 2 upon x plus 1 all square, is equal to the base to this value here, 2 to the power of 2, which of course is 4. So this can be rewritten now as, so this is 4, so 4 times, so this is 4 into x plus 1 all square equal to 2 times x plus 2. Alright, so this becomes 4 x plus 1 all square into 2. Can I just factor out 2? Alright, and if I factor out 2, I could rewrite this as 4 x plus 1 square minus 2 times x plus 1 is equal to 0. And now of course I can factor x plus 1, right? Since x plus 1 is a common factor. So if I factor x plus 1, what I end up with here, factor x plus 1 from here, I'll be left with 4 times x plus 1, which is 4x plus 4. And I factor x plus 1 from this term here, I will be left with just minus 2. Let me just continue over here. So in the end now, I'm left with x plus 1 in one bracket and 4x plus 2 in the other. And of course, we saw we can equate both brackets to 0. So x plus 1 equal to 0, which means x equal to minus 1. Or 4x plus 2 is equal to 0, which means 4x equal to minus 2, which means x equal to minus 2 upon 4, which is minus half. So the solution, minus 1 and minus 1 and minus half. One thing to note though, I think we would have to omit this solution. Reason being, so the solution will just be x equal to minus half. Reason being, let's look back at the problem again. Here was the original problem. Notice, if the value of x is minus 1, in the bracket what you'll have is log 0. And log 0 is not possible, no matter what the base is. So if x is minus 1, this bracket will be 0. This bracket will also be 0. And log of 0, that's a matter, right? That's undefined, regardless of the base. So x equal negative half will be the solution that we use, alright? So let's move on. So in question 2, part A, we're asked to sketch the inverse of the function above in the diagram above, and we're asked to use a graphical method to show that the function is bijective. Bijective means the function is injective and also surjective. Let's sketch the inverse first. So the inverse, note the inverse of any function is basically a reflection of the line y equal x. So what is this choice is to draw the line up the graph of y equal x. The graph of y equal x will cut through 1, 1, 2, 2, 3, 3, and so on. Alright, negative 1, and so on. So the graph of y equal x would look like that. So forgive me, I'm not using a ruler, but you should use a ruler when you're doing this graph. It's a straight line, y equal x. And of course, it cuts, alright, also Alright? So the graph of y equal x will look like that. Of course, a straight line. Good? Now, let me do the top part first. So of course, f of x is basically a reflection in this graph. So we want to reflect this graph in the line y equal x. Now, when you reflect a point in the line y equal x, what happens? The coordinates switch places. So for example, look at this point here. 2, 4, 6. Let me just leave this. So this is 2, 4, 6, 8. 2, 4, 6, 6, 6, 8, and of course 10 above. So if you know what this graph passes through the point 2, 8, so the reflection in the y equal x will bring it to the point A2, and so on. Alright? So the graph would look something like this, reflected in line y equal x. It will look something like this. Right? So there's a reflection in line y equal x. So this will be f inverse x. So this is f of x, f inverse x. Now on the other side, let's do it on the other side. So here's a graph. Notice this graph passes through this point is what? -2, -10. So if we reflect it in the line y equal x, well, no, this is actually -8. -2, -8. So -8, interchange those points, we end up with -8. -2, which would be approximately here, right? Which would be about here. Right, so this graph would pass through this point, of course. So it should look something like that. Alright. Good. So that's how you reflect a point in line y equal x. The coordinates swap places. So where this is -2, -8, it would be -8, -2. So the inverse function would pass through the point -8, -2. And we are also asked to prove that the function is bijective, meaning it's injective and also surjective. And how do we do that? We do what we call a horizontal line test. So any horizontal line drawn, notice the original graph in black there. Any horizontal line drawn will cut the curve. Only once, which prove it's bijective, 1-to-1. Sorry, which prove it's injective, 1-to-1. Any horizontal line drawn will cut the graph only once, that prove injectiveness. And of course, the fact that it cuts it always means that the graph is surjective. Alright? Let me just write a statement there. So, note, we'll just write, so any horizontal line drawn will cut the curve once. Right? Hence, curve or function is injective and also bijective. Alright? Therefore, the function is injective and also surjective, sorry. Hence f of x is bijective because it's both injective and surjective. So injective because it's a 1-to-1, it cut the graph. It will cut the graph only one time. It's surjective because at least it will always cut the graph. Alright? Regardless of where you draw the horizontal line. And of course, the function will be bijective since it's both injective and surjective. Now, to do part B is a proof. So the modulus of x minus y. Note that the modulus of x minus y. So I'm focusing on the left hand side. Notice the modulus of x minus y is greater than or equal to. It's one of the properties of the modulus of x plus modulus of y. Let's deal with the left hand side now. The right hand side, sorry. Now we have the modulus of x minus z. Modulus of x minus z is greater than or equal to modulus of x plus the modulus of z. Also, modulus of z minus y is greater than or equal to the modulus of z plus the modulus of y. Now I'm going to add the last two. Alright, so I'm going to add these two. And what I'll end up with is what we have on the right hand side of the proof, which is the modulus of x minus z plus the modulus of z minus y. So we add these, so we're going to add the right hand side also. It's add modulus of x plus modulus of y. And then we have 2 mod z here, right? So plus 2 times the modulus of z. So we can do some logical reasoning now. So note that, let me just compare, just circle what I'm comparing. So I'm comparing the modulus of x minus y with the result of the summation here. Let's compare these two inequalities. Now what you'll notice, so the modulus of x minus y is greater than or equal to mod x plus mod y. And this summation here, so notice, modulus of x minus y, mod x plus mod y. And in this summation here, has the same mod x plus mod y plus an extra term, 2 mod z. So it's logical to deduce that the modulus of x minus y would certainly be a smaller value than the modulus of x minus z plus the modulus of z minus y. And you get that by just comparing the two terms. Compare mod x minus y, mod x plus y. Compare this term here at the end here. It has same mod x plus mod y plus 2 times another positive value. So which expression would be smaller? At least. This would be smaller, right? And compare, this would be smaller. At least. And this would be larger because of the extra term here. 2 mod z. So I guess we can safely conclude that mod x minus y is less than or equal to this term here. Alright? So when I compare this to this, then mod x minus y is certainly smaller when I compare. Hence the proof. Next problem, solve the inequality. Notice we have 6x minus 2, a modulus, so it can be, remember the 6x minus 2 can either be positive or negative, right? So we'll begin with the positive, 6x minus 2 plus x squared less than or equal to 5. And over here, let me just separate it. Over here, of course, it can be negative. 6x minus 2 plus x squared less than or equal to 5. So we have a pair of quadratic inequality. So let we just simplify or group everything on one side. We have x squared. Then we have positive 6x. And if we subtract 5 from both sides, we have minus 7. And of course, this can be easily factorized. So we can factorize. Watch my video on factorization. Easily factorize. So x, and of course, positive 7 minus 1. It's less than or equal to, so x is between the two values. So x is between less than or equal to this larger value, greater than or equal to the smaller value, which is minus 7. Alright, since positive 1 and negative 7 are the critical values, if you equate these values, these brackets to 0 and solve, you'll get 1 and minus 7. Over here, we have minus x plus 2 plus x squared, and we can subtract 5 from both sides. We have minus 5 over here. So we have a quadratic x squared minus 6x minus 3 is less than or equal to 0. Now to get the critical values, we'll certainly need to use the quadratic formula, since this cannot be factorized. So the quadratic formula, let's use this. And this is to get the critical values. That will make the expression 0. So A, notice A is 1, B is minus 6, C is minus 3. So minus B will be positive 6, right? Double negate the 6 there. B squared, that's minus 6 squared, which is 36. Now the value of A is 1, and the value of C is minus 3. So it's minus 4 times 1 times minus 3, that's positive 12, upon 2A, which is 2. So x equal to 6 plus or minus the square root of 48. Now what's the square root of 48? That's 6.928. So I'm using 3 decimal places. So let's extend this. So x would be equal to, well, the critical values on this. So critical values. So 6 plus 6.928 upon 2, or 6 minus 6.928 upon 2. So x equal to, so without the first one would be 12.928 divided by 2. That's 6.46, and the other critical value, so 0.928, 0.464, about 0.46. Alright, which means the solution here for this inequality is x is between. Alright, since it's less than or equal to x is between, so x is, by the way, it's negative, right? Negative. So x is between less than or equal to the larger value, which is 6.46, and greater than or equal to minus 0.46. So hence the solution so the final solution, so therefore, the final solution so x is between, so the critical values are what? 1. So the 6, so this 1, alright, so if you use a number line here, 0, notice 6.46, alright, and then there's 1. And then there is minus 0.46, and then there's minus 7. So the inner value here, so x is between these two values, less than or equal to 1, greater than or equal to minus 0.46. And to test, you can, of course, you can use any values between 1 and 0.46 and 6.46, or between 1 and negative 7. You can test those in the equation and see if they work. Let's test, for example, minus 5, to see why minus 5 is not a possible solution, or even positive 5. These are not possible solutions. Let's see, if x is 5, let's say x is, say, 5, and 6 times 5 is 30, 30 minus 2 is 28, 28 plus 5 squared, is that less than, is that less than positive 5? No, it's not. Let's check minus 5. Minus 5, 6 times minus 5, that's minus 30. Minus 2, that's minus 32. Modulus, so it's positive 32. Plus a square term, you get a positive value. It's certainly not less than or equal to 5. So the only solutions that will work, that will fit this inequality here, will be the values which are less than or equal to 1, but greater than or equal to negative 0.46. Let's try 1, since it says that 1 error. Let's try 1, since it could be equal to 1. If x is 1, 6 times 1, that's 6. Take away 2, that's 4. 4 plus 1 square, that's 5. Is 5 less than or equal to 5? Yes. If x is 0, 6 times 0 is 0. So you're left with negative 2. The modulus of negative 2 is positive 2. Plus 0 square, which will be 0. Is that less than or equal to 5? Yes, it is. Alright, so these values you can always check them. Alright, so the only solutions that will work would be the x values, which are between 1, less than or equal to 1, greater than or equal to minus 0.46. These values will satisfy the inequality, certainly. So part C is about some cubic polynomials here. Determine the equation whose roots are so. So we are told that alpha, beta, and gamma are the roots of this polynomial, this cubic equation there, which means that, remember, the sum of roots, so alpha plus beta plus gamma, the sum of roots, remember, is negative b over a. So negative b, so a, b. So negative b would be, remember, b is a coefficient of the x squared, right? So a, so negative b will be positive 1, right? Over a, which is 2. The product, alpha, of the roots, alpha, beta, gamma, the product is negative d over a. And d would be the constant. In this case, the constant is 1. A is 2, so 1 over 2 again. And the sum of the products, so alpha, beta, gamma, plus alpha gamma is equal to c over a. Now, what is c? C is a coefficient of the x. Notice that there's no x term there. So the coefficient, of course, would be 0 over a. So it's 0 over a, which is just 0. Good. So we are to use these to determine the equation whose roots are 1 over alpha square, 1 over beta square, 1 over gamma square. So let's do that. Now, the equation whose roots are 1 over alpha square, 1 over beta square, and 1 over gamma square. This equation would be x minus 1 over alpha square into x minus 1 over beta square into x minus 1 over gamma square. So if the equation, if equation has these roots, then these would be the cubic equation. Now, of course, we can expand. And if you expand, what you will find out is that you'll have the terms will be x cubed minus, and the coefficient for the x square would be the sum of the roots, which is 1 over alpha square plus 1 over beta square plus 1 over gamma square. So these will be the coefficient for the x square, and the coefficient, well, negative, right? Yeah, so that should be minus. And the coefficient for the x would be the sum of the products, which would be positive. So we'll end up with 1 over alpha square times 1 over beta square plus 1 over beta square times 1 over gamma square plus 1 over alpha square times 1 over gamma square times x, and the constant would be the product, the negative product minus the product, which would be 1 over alpha square 1 over beta square times 1 over gamma square equal to 0. So, in other words, to find this equation, we need the result of all the brackets there. Alright, let me just bracket that. So let's do that. I begin with the final bracket here. So 1 over, should be 1 over alpha square. So alpha square. I have gamma square twice. Alright, so 1 over alpha square times 1 over beta square times 1 over gamma square is equal to, now law indices I can just, so alpha square times beta square times gamma square, that's 1 over alpha beta gamma all square. So it can be rewritten as that certainly. Now the product of alpha beta gamma, remember the product of alpha beta gamma was a half. Alright, the product of alpha beta gamma was a half. Good. So this means that reciprocate this. So 1 over this would be, of course, be 2. So that would be equal to 4. As 1 divided by a half, which is 2, and 2 squared 4. So we have our constant. So this will be the constant, right? Which will be the last bracket. Constant. Let's move on now to the coefficient of the x square. Which would be the first bracket here, 1 over alpha square plus 1 over beta square plus 1 over gamma square. Let's try to simplify this expression. We can have a common denominator, which is alpha square, beta square, gamma square, and we can use the whole idea of equivalent fraction. Now if I want to make this denominator, if I want this alpha square to become the denominator of beta square, gamma square, I multiply numerator and denominator by beta square, gamma square, right? For the middle term here, if I want this to have a denominator, I would need to multiply by what? Alpha square and gamma square. And I have to do the same to the one also. And here, alpha square and beta square, right? Now, very importantly, note that we are given some information here. So notice we are given this result here, so we can use this result here. Notice alpha beta square, alpha gamma square, beta gamma square is equal to all of what we have here. Alright, alpha gamma, beta alpha plus gamma alpha all square. Let's write it out. So this is equal to, let's bring it over here. This is equal to alpha beta plus beta gamma plus alpha gamma all square minus, let's just go back to it. Oh no. Minus 2 alpha beta gamma plus the product, right? It's times the product times the sum. So minus 2 times alpha beta gamma, and then we have the sum inside. Alpha plus beta plus gamma. Alright. And all of this is, remember, denominator alpha square beta square. Let me just write it different. Let's write the denominator different. Since all of them have a square term, so it's alpha beta gamma all square. And all these values we have. Let's plug them in. No cram for space here. Let's plug them in. Alright. Now the sum of the product, alpha beta beta gamma alpha gamma all square. Let's go back to what we have that result here. Here it is 0. That's 0. Alright. So that is 0. So 0 square is 0. Minus 2 times the product times the sum. Let's check what the product and the sum were again. The product was half and the sum was half. So it's half times half, right? Which is a quarter. So 2 times half times half all upon this, all upon the square of the product, which was, so the product, remember the product was half, so we square half. Alright, now this works out to be what now? Let's continue. This works out to be, the numerator would be minus 2 times half. That's what, minus a half. Divide by, the denominator is a quarter, divide by a quarter. So that's minus a half times 4, which is minus 2. Which means that the coefficient of the x squared is minus 2. Alright, so next we want now, the last thing we want now is the coefficient of the x, which is the middle bracket, the second bracket. Coefficient of the x. So you have in the bracket 1 over alpha square, beta square, and so on. So let's do that. So the coefficient of the x now, so coefficient of the x, remember, it's 1 over alpha square, beta square, plus 1 over alpha square, gamma square, plus 1 over alpha square, beta square, gamma square, right? That's the other one that's remaining. Beta square, gamma square. Let's try and simplify this. So if we should simplify, the common denominator would be what? Alpha square, beta square, and the gamma square, certainly. So to get this to be alpha square, beta square, gamma square, we multiply numerator and denominator by gamma square. So we'll have gamma square here. To get this to be alpha square plus, well, the same denominator as this, so we'll multiply by what? Beta square, numerator and denominator, equivalent fraction we're using here. And then to get this to have the denominator down here, we'll multiply by alpha square, top and bottom, right? Now, the numerator, we should recognize that. So by the way, let me just fix up the denominator. Now the denominator can be written as alpha, beta, gamma. Alright, all square, since all terms are square. Now, alpha square, beta square plus gamma square, what is that equal to? Notice the question gives us a bit of help here. Notice, so this uses here. alpha square plus beta square plus gamma square. Notice what is equal to the sum of the sum of alpha, beta, and gamma, all square minus 2 times the sum of the product. Alright? Let's go back to the question. So alpha square plus beta square plus gamma square is alpha plus beta plus gamma all square minus 2 times the sum of the product. So alpha beta plus beta gamma plus alpha gamma. And we have all these values. Remember, the sum was half, so half square, right? Minus 2 times what we have in the bracket was 0, right? And of course the product was half again, right? So half square. So half square upon half square divided by itself is 1, right? So the coefficient of the x is 1. So therefore, let's write the solution now. Therefore, cubic equation. Therefore, the cubic equation that has 1 over alpha square, 1 over beta square, and 1 over gamma square as its roots is x cubed. This the 1 represents the, let me just go back. The 1, let me just go back to. Alright. So here it was. Notice the constant was 4. Let's make a note of that. The constant was 4. So it's x cubed. The constant was 4. Well, this bracket would be minus 4, alright? Because whatever you have in the bracket there came to 4. The coefficient of the x and the x square, what are they? The coefficient of the x, I think we found it. The coefficient of the x square, we found it to be minus 2. So it will be positive 2, since it's negative the bracket, right? And the coefficient of the x was, 1. 1x. So the equation would be then, the equation would be x cubed plus 2x squared plus x minus 4 equals 0. So the first bracket, the value was minus 2, so the minus positive 2. The second bracket, which was 1, and the final bracket there, the value was minus 4. So this would be our solution. Next problem, show that sine 2 theta minus cos 2 theta. So it's a trig proof, right? So let's do this proof. So let's begin with the left hand side. So the left hand side is equal to sine 2 theta. No, sine 2 theta, the identities, 2 sine theta, cos theta, minus, and cos 2 theta. I'm going to use the identity for cos 2 theta. You're going to use 1 minus 2 sine square theta. And we have our plus 1 outside there. The denominator, so I'm using 1 minus 2 sine square theta for cos 2 theta. And sine 2 theta, that's 2 sine theta cos theta. And then we have our minus 1 out here. Good? So I want to show that all of this will come to sec 2 theta plus tan 2 theta. Let's see, let's expand. So we have 2 sine theta cos theta. We expand this bracket, we'll have minus 1 plus 2 sine square theta plus 1 upon 1 minus 2 sine square theta plus 2 sine theta cos theta minus 1. Notice in both the numerator and denominator. Alright, negative 1 plus 1, that's 0. And this 1 and this one, that's 0. Alright, so we could factor, and in the numerator we could factor 2 sine theta. So we factor 2 sine theta. 2 sine theta factored from here will be cos theta. And 2 sine theta factored from here will be sine theta. All upon, and then, alright, so I can factor 2 sine theta. So 2 sine theta factored from this term here would be cos theta. And factored from this term here would be minus sine theta, right? Notice when you expand the bracket, you get the same thing. So 2 sine theta into itself, that's 1. So what we really have is cos theta plus sine theta upon cos theta minus sine theta. One thing we could do is multiply by the conjugate of the denominator. So the conjugate of the denominator is cos theta plus sine theta. So for the fraction to remain equivalent, we have to do the same to the numerator. And what we end up with here now. So let's expand the denominator first. Notice the difference of 2 squares. So when you expand, that's just cos squared theta minus sine squared theta. Good. And above here, notice cos theta plus sine theta times itself. So the cos theta, let me just write it a little neater. So if I expand it, the numerator will be cos times cos, that's cos squared. And then sine times sine, that's sine squared theta. Another term will be 2 sine theta cos theta. Now recognize an identity. Cos squared plus sine squared, that's 1, right? 2 sine theta cos theta, remember that's sine 2 theta, that's a trig identity. And then cos squared minus sine squared, that's cos 2 theta. Right, so notice what you have is 1 over cos 2 theta plus sine 2 theta over cos 2 theta. So I break up the fraction. So 1 over cos 2 theta, 1 over cos, that's sec, right? So that's sec 2 theta. And then sine over cos, that's what's tan. So tan 2 theta. Alright, this is what the right hand side is equal to. Alright, and of course this proof quite easily done. Notice the right hand side was sec 2 theta plus tan 2 theta, right? And we are able to comfortably do this proof. Let's move on to part B. Part B, hence or otherwise determine the general solution of this. Now remember, what you have on the left hand side here, we just prove that that is equal to sec 2 theta plus tan 2 theta. We just did that proof. Alright, so we can equate it to 0. Since all of this on the left hand side, we prove it was equivalent to sec 2 theta plus tan 2 theta. Alright, which means that we can easily make the angles be theta as long as the angles are the same. That's the key thing. Alright, now sec, what is sec? Sec is, I must be, so this is sec theta equal to, let me, different here. Sec is 1 over cos, right? So 1 over cos theta plus sine theta over cos theta is equal to 0. So 1 plus, we can put everything over 1, denominator, right? 1 plus sine theta over cos theta is equal to 0. Which means that the numerator would have to be 0, right? So hence 1 plus sine theta is equal to 0, which means that therefore sine theta is equal to minus 1. But remember, we're asked to find the general solution. Alright? Now, the sine of which angle give you -1? The sine of is 270. Sine of 270 give it -1. So theta would be 270. We can write 270 as 3 pi over 2. Alright, but we want a general solution. So it's plus 2n pi. Alright, so 270, 3 pi over 2. So every complete rotation, sine of that angle would give you -1. Alright, so our general solution would be this. So, part B, given that cos A is 3/5, so cos A remember cos, we call this A. Remember cos is adjacent over hypotenuse, right? So cos A adjacent 3, hypotenuse 5, so this would be 4. Alright, so that's right. So if cos A is 3/5, it means that sine is opposite over hypotenuse, so 4/5. Alright, and sine B is 3/4. So if sine B, let's draw a right angle triangle there. If sine B is 3/4, now call this B. Sine is opposite over hypotenuse, so 3/4 will be 3 over hypotenuse 4, which means the adjacent, using Pythagoras theorem, this side will be the square root of 16 minus 9, right? So this will be the square root of 7. So if sine B is opposite over hypotenuse, means that cos B is adjacent over hypotenuse, so it's root 7. Just a moment. Yeah, root 16 minus 9. Okay. So cos B is adjacent, is root 7 over hypotenuse, which is 4. And we're also find sine 2A. Now sine 2A identity is 2 sine A cos A. So that will be 2 sine A, that's 4/5, times cos A, that's 3/5. So if we times this, so 2 times 4, that's 8. 8 times 3, that's, so 8 times 3, 24. So it's sine 2A would be 24 upon 5. Upon 25, sorry. Alright. Alright, so part B, so the second part now, we also find cos A plus B. Alright, now cos A plus B. Cos A plus B is cos A cos B, using the addition formula for trig, minus sine A sine B. Now cos A, what was cos A and cos B? Cos A was 3/5 and cos B was root 7 upon 4, minus sine A 4/5 and sine B was 3/4. Notice both of them are the same denominator of 20, so we can just put everything over 20, right? So 3 times root 7, that's 3 root 7, minus 4 times 3, that's 12. So of course we can leave our solution like that. Part C, we also solve this equation. Now of course we can rewrite, so we can let R sine theta minus alpha be equal to the equation on the left hand side here, sine theta minus root 3 cos theta. If we expand, we would have R into sine theta cos alpha minus sine alpha. So we alternate, right? cos theta sin alpha. And that's equal to sin theta minus root 3 cos theta. Now we can equate coefficients. Now if we create coefficients for sin theta, so sin theta, let's do for sin theta. For sin theta, we'll end up with r cos alpha on the left hand side, and on the right hand side for sin theta, the coefficient there is 1. Alright? We can equate coefficient for cos theta. For cos theta, the coefficient there is on the left hand side, well, for negative cos theta, right? On the left hand side there is r sin alpha, and on the right hand side there is root 3. Alright? Note, if we divide, so we call this equation 1, equation 2. Note, if we divide equation 2 by equation 1, so if we just divide equation 2, so r sin alpha, put at the top, equal root 3, and the other equation 1, r cos alpha equal 1. If I divide, I will get tan alpha is equal to root 3. So if tan alpha is equal to root 3, then alpha would be 60 degrees. Alright, or if you're using pi radians, it's pi over 3, right? You can multiply by pi over 180 to convert it to pi radians. Now, I need the value of r. Now we know that r, remember r, we can use whichever equation. We call that r cos alpha is 1, right? We know alpha is 60 degrees, right? So r times 60 degrees, cos 60 degrees is 1. Now cos 60 is a half, right? So half r is equal to 1. If we time both sides by 2, then r is equal to 2. Alright, which means therefore, so recall that, so r sin theta minus alpha is equal to all of this. Alright, which is also equal to 1. So we can equate r sin theta minus alpha equal to 1, since it's equal to sin theta minus root 3 cos theta. Alright, so we can equate r sin theta minus alpha is equal to 1, and r is 2, and theta alpha was 60 degrees, right? Equal to 1, which means that sin theta minus 60 is equal to half if I divide both sides by 2. Now, which angle do you sin to get half? So theta minus 60 is equal to shift sin inverse half. That's what, 30 degrees. That's 1. Remember sin is positive in two of the quadrants. So the other angle would be 150 degrees. Right? Which means that theta, if you add 60 to both sides, the theta would be equal to 60 and 30, that's 90 degrees. Or 60 and 150, that's 210 degrees. Theta. But remember, I think we're given a range for theta. I think we're told that theta is between negative 180 and 180 degrees. Alright, so we'll show out one of the values. So we'll show out the 210, since this is out of the range. So theta is 90 degrees, or the solution, or If you want to write it in pi radians, that's pi over 2. Pi over 2 radians. Alright, either would certainly work.